And currently he's lecturer there and also doing this postdoctoral research there. And he did his PhD from the university only under the guidance of Professor Cho. And his research area includes the finite element analysis, composite material, failure criteria, etc. And he has published a lot of papers, so you can check on his Google Scholar, right? So now, sir, over to you. Please start.
Thank you, Narendra sir. Thank you, Vikas sir. Thank you, NIT Jalandhar, for this good GIAN course and initiative to learn the new things for the composite material modern era. So, my name is Kumar, and I will show you the basics of the finite element analysis and the few things in the abacus and the advanced how to install the subroutine kind of things, and then we will show some of the glimpses of MATLAB, how to do the finite element things in the MATLAB, because sometimes happen the students has abacus student version has limited things, right? But MATLAB is a free of software for the students, so you can use the MATLAB for the analysis thing as well. So I will show you some GUI things in the MATLAB as well. But abacus has the paid version, so that will we show in the research institute. Abacus is there everywhere, so you can take a benefit of that as well. And license version and the student version has limited like nodes and the elements, so accordingly you can use the software. So finite element analysis, as you know, we have to. Okay, the PPT, yeah, here.
Just wait. Yes.
Yeah, okay. So let's start with our basics of finite element analysis. So finite element analysis, we have to deal with the finite geometry, right? Like there is a quantum geometry, like a full geometry, physical model, but we have to convert it into the finite parts, right? So first purpose is to create the geometry, right? First target is to create the geometry. If this is simple geometry, we can create in the analysis software as well, right? Directly. Second part is like create the geometry in analysis software if it is simple geometry, right? Suppose it's a complex geometry, then you have to go the modeling software. Modeling software. That is kind of SolidWorks, CATIA, these kind of things, right? ProE, these kind of things. So if geometry is complex, then you can model there and import here. If geometry is simple, you can directly model and analyze it, right? So the second thing, when you model the geometry, what you do, you suppose you model this one, right? It's a continuum body. This is a one continuum body, right? One continuum body. It's continuum things. Continuous, you can say, continuous body, right? So if you analyze this body, it will give you just one equation, right? This is a one model, right? Just one model. So if you analyze this is not possible to analyze this as a physically. But when you have to analyze this, what you have to make? You have to make it discretize, right? Discretize. So you have to change the shape into discrete manner. And this discretization is very important, because you have to cover the shape of the model. You have to cover the shape of the model by the discretization as it is. You have to cover this chamfer, flats, everything with the meshings, discretizations. So that called a meshing, right? And that meshing is very important phenomena in the finite element analysis, because it's an elemental analysis, right? So this is do not work as the continuum model, it works on the elemental model, right? So each of element has a one equation. This element one equation, this element one equation, this element one equation, this element one equation. Each and every element solve the equation and make a integrations. So this is kind of partial differential equations solution, right? So you have to solve the partial differential equation on each of the element. Element can be different type, we will see it, right? So first thing, create the model either in simple way, in the analysis only. It can be the abacus, ANSYS, it can be the NX, Nastran, and many more, right? The popular one is abacus and ANSYS, right? Those were the popular one. So you can create here, if it's a complex one, you can create the model, import, and the importing category is IGES, STEP. These are the importing categories. Then after importing, what you have a purpose? It's a physical model, it's a continuum model, continuous model. You have to make a discretized one, right? Then discretized, you have to make a massing. That massing means you have many elements, and each element has nodes, right? Each element has nodes. So what software does, and we will cover the basic finite element methods also, how the finite element and works behind the software, I will cover that also, right? But before that, I want to show you the glimpse of how it goes on in the software, right? And the backside background, what has happened, we will cover that. So in the nodes, what happened? They solve the partial differential equation, each node. Then from node to goes the element, then all element will sum up, then make a integrations, right, at the volume. What happened here? It makes the energy, right? Energy. So every physical model has an energy, right? Every physical model, there is an energy. That is called a potential energy. Potential energy, right? There is potential energy. So what is the purpose of us to analyze the model? We have to make the minimization of potential energy when we converting the physical model. Suppose this is a room, right? We have to analyze it. We will convert into mass, and we will think what we are doing by the discretization, it should be same as the physical model. So we have to make the as much as minimum, we are making equal to 0. Potential energy inside the model, we are making equal to 0. So this is the approach of the analysis finite element method. There is a different method, Ritz-Relay method, Glarkin method, they calculate the analysis, right? But the purpose behind that is we have to minimize the potential energy. That means this energy will be 0, equal to. That exactly will not be 0, because we can say approximation. This is always approximation, right? So finite elements is a approximation. That is not an exact solution, right? This is not an exact solution. This is an approximate solution, twice the exactness. So we assume that potential energy is a minimum. That means it's a twice 0. We assume is exact 0. That's why it's an approximate solution. Okay? We can make it up to 99% accurate, up to 99.99% accurate, depends on the implicit explicit analysis. We will check it. Okay? We will check it. But the important thing here, minimization of energy equal to 0 covers from discretizations, because as much as you discretize, the finer the mass, that will give you the better quality, right? But there is also the mass sensitivity work. When you solve it, you have a different result. Suppose you are making 4 elements. Suppose I'm just make it again. We will cover this topic again, potential energy one, right? Before that, I want to just show you the mass sensitivity one, how it works, right? So see, suppose you have this model, right? Simple plate, and you are doing the bending analysis, right? So suppose those cantilever, just applying here like this. If you are dividing just 3 element, right? 3 element. So it's just covering only the 3 equations, 3 elemental equations, right? 1, 2, 3, and a summation of the shape function and something like that, right? But this will not give you accurate answer. This, suppose exact one this, it will give you maybe this, right? Then you have divide again. So you have to make the mass sensitivity work up to the accurations, right? You have a theoretical analysis, right? Theoretical. You know the theoretical is an exact. You have a formula of bending of plate, cantilever, beam, right? So you can make what? Theoretical. You have a result, something, suppose 3 megapascal stress is coming, right? When you do the finite element, suppose you have a 3 element, maybe you got the 2 megapascal, right? When you have a 5 element, maybe you got the 2.2 megapascal. You will increase the elements. Then you reach up to the point, maybe up to 20 element, it will give you the 2.98 megapascal. So that means this 20 element reached to the level of the theoretical result, right? So you, yeah, we have mass optimizations. In the software, we have mass optimization algorithms so that we can decide they corner and chamfer cover properly to give the, maybe if we cover this properly by tetrahedron, the combinations. Massing has different combination, we will see the elements as well, right? We have a triangular element, quadrilateral element. So triangular, quadrilateral, we have a, in the 2D, right? In the 2D, just 2 type of element, and in there also we have a first order element, just 1 node like this. Second order element, we have a node like this here also. So as much as node increase, solution accuracy will increase because element order is increasing, right? That will take longer time to run because large equations. We will check why longer times needed when we work with this. Why? Because it's an inverse analysis, right? Matrix inversion happens when you do the implicit one. But we will check why explicit chosen when we do the impact analysis or drop testing and crash testing. We do explicit analysis, right? Why those explicit we go and why we do implicit when we have a less velocity, quasi-static one. So we will check those things later on. So we will go slowly. So now we reach up to the point and we can say this mesh, right? Suppose this is a graph, something like this, right? This is the element number, so 5 element, 10 element, 15 element, 20 element. So when you write the article also, into the FEM analysis article, you have to include the mesh sensitivity. It will give you a publication chance better. Because if you write the mesh sensitivity analysis, they understand you check the discretization properly for each and every scenario. So they know your optimization is correct for the mesh sensitivity, right? So there is stress value, so you can reach here, then it will stagnate. So up to here, solution going to the, this is suppose accurate one, this value. So here it will go and accurate, then after some point, how much elements you increase, it will give you the same result. So it will be stagnate, right? So you reach the point, suppose 20 elements give you the 25 element give you exact 2.99995 megapascal. So it is your stagnation point, 25 element. Up to that you will increase 30, 35, approximately same. Maybe sometimes it can go down or up, but it will be approximately same. Time will longer, so you have to reach the point of optimization where exact solution can reach to the theoretical solution. The approximate solution can reach to the exact solution. This getting the point? Okay. Now we understood the discretizations. Our point, create the model, mesh the model is finished, right? This one is finished. Now we will come to the this one. But before that, you understand this physical model, right? This physical model just a continuous model. We discretize the model. That called a mathematical model, kind of partial differential equation. So in the finite element analysis, we have to solve the partial differential equations and then make integrations. Okay. So this is a finite element analysis, so mathematical model, finally last. But before that, now I showed you the one term, potential energy zero. Potential energy zero when we solve the system, right? How it works, we will see it. So see, I will show you the how we calculate the steps, background steps. Then we will see the abacus analysis. Before that, I want to show you background how it works, right? How we assume that potential energy is zero, how it works, and how we calculate the final stress result. Because lastly, we have to make the stress result, right? And then report how we reach the stress result. Okay, thank you. They will watch. Okay, so see, let's assume some domain, right? Let's assume some domain. There is some point P has x, y, z coordinate. Okay, just assume this is I am showing how the analysis works behind the process, right? We have to just see how it works and how we reach to the stress. How we calculate the stress. We have to reach this point, right? Final result is stress result, right? How we reach at there. We have to work for this. Okay. We have to reach to there, but how we reach there, we will check by the background process. Then we will see in the software how we do. So we have to reach here. See, this is the point in P in the domain. Suppose this is a domain. Let's see, this is the, okay. This is a domain, right? This is one domain. Or the physical model you can say, this physical model, right? Here inside this point P has x, y, z coordinate, right? Suppose we apply some force F. Right? Let's see volumetric force, gravitational force. Either you apply the body load, something like that, right? Apply the force. So suppose the deformation vector, U vector, you think it's a U, V, W. It will deform, right? When you apply the force, it will deform, right? Transpose means column vector, U, V, W. Okay? When you apply the force, this will be deformed, right? So this is a deformation U, V, W. When the deformation done, what the strain? Change in length upon original length, right? There will be strain. When it deform, there will be strain. Change in length upon original length. X direction, Y direction, Z direction, shear strain, right? So this is the X direction deformation, Y direction deformation, Z direction deformation, right? So this will create the strain, X direction strain, right? Y direction strain, Z direction strain, then shear strain, right? So this will create the strain, right? So we have a deformation, then strain. This is due to, we have a different kind of load, either the body load or volume load, traction load, surface load, this is called surface load, right? And either the point load. This is the three kind of load we have generally. Generally we have three kind of domain of load. Volume load, surface load, either the point load. So that can be denoted, suppose volume V, F dV, right? Something like that, F force. This is traction force, we have a T. Point load, we have a P. So we have a three force, give the deformation. Any force can give the any deformation, right? The deformation can produce the strain because change in length upon original length, right? Change in length upon original length. So this will give you the strain. So suppose we are calculating the X strain, right? But the strain is like that, right? You see, if you do this, if you apply the load here, this will go like this, right? So this direction load can cover the here and there as well, right? Both direction, due to this called a Poisson one. So those each are connected to each other, right? Everything is connected to one to each other. So Poisson one make this scenario, right? So we have a everything connection. Now this, if we go to the deformation to strain, we have three things. That makes X direction strain. Now, so the Ex will be what? There is Ex, Ey, Ez, tau xy, tau xz, tau yz, right? This is the we have. So this is nothing but del u upon del x. This is del b, b is there, right? Del b upon del y. This is del w upon del z, right? And this is del, so y x. So x means u, right? Upon y. This is not working. So y u upon y, okay? Plus x means del v upon x, okay? So please remember, because this is a shear strain, so when you write u, y, v, x, okay? This is the tau xy, tau xz, del z upon del u, okay? Del x, sorry, del w upon del x plus del u upon del z, okay? So you understand how to do this, right? So shear strain, xz means wx, uz, okay? X, u, z, z, wx. So this is shear strain. Here tau yz, the same way, right? Tau yz is del, so z means what? W upon y, del y, okay? Plus y, so del v upon del z, okay? So this is the way to get the strain, right? This is strain definition. Terms of the displacement, we got the sixth scenario of the strain, okay? So we have a displacement, we have a strain one, right? We got this. Now stress, this is a tensor, actually we are creating the tensors. Finally, lastly you will see this kind of things, stress, E, epsilon. So this is a fourth order tensor, second order tensor. Ultimately you will reach here, slowly we will go, right? Slowly we will go. But now we are reaching here. When we reached here, now we have to come to stress. What is stress? Stress is nothing but E epsilon, right? Hooke's law, right? Hooke's law. So this gives you the, but this is for the elastic region. Right? Please remember. But why we are saying the elastic region? Because we are working for the infinite small deformation. We are finite small deformation, sorry. We are working for the very less deformation. We are this formula, all formula is for the very less deformation, right? Finite deformation. Infinitesimal, we say, infinitesimal deformation, less deformation. These are applicable when the deformation is less, okay? That's why they work for the elastic region. And that's why all those correct. Somebody says you this formula, long deformation, large deformation, no, not right. Not. This formula is for the very less deformation. That less deformation creates the elastic zone, and that elastic zone has all values, all values. So if you see the stress strain diagram, it's like this, something like this, right? For the brittle material, ductile material, something like this, right? So composite one, something like this. So like this something. So this is the elastic one. We are focused in this region, elastic one, linear region, okay? Linear region as our target. So whenever we works on this kind of formula, these are just for the infinitesimal small deformation, right? Very less deformation. Please remember this. Now, this is the strain you understand, this you understand. Now, come to the stress point, right? So you understand the Hooke's law, right? Then stress is what? So we have a, now force. Strain you understand, let's do the force summation. So we have a sigma x, suppose you calculate the strain, right, this way, and that has a relation, right? Strain has relation with stress is this way, right? Ex is equal to sigma x upon E minus nu sigma y plus sigma z upon E, right? This is the way, right? This is the formula to calculate stress and strain conversion, right? Okay, so this is the epsilon, right? This is the E. Getting the point? Getting the point? The Hooke's law. This way we are getting the stress strain conversion things. So you understand the things, right? Tensors. But now let's need the force system, because ultimately I told you we have to reach the potential energy. Target is potential energy, right? Because when we solve the problem, our purpose is to minimization of the energy as to 0 to 0 to 0, right? When we reach to 0, that means we are reaching to the exact solution, right? Our target is this one. Potential energy should be 0. And that is nothing but what? That is nothing but summation of strain energy plus work potential, right? Potential energy is nothing but strain energy plus work potential. And strain energy nothing but stress and strain. And this is loading applied. So I told loading is, see the correlation all. Loading is body load, traction load, point load. Body load, traction load, point load. Strain energy is strain, stress, right? This is nothing but 1 upon 2 sigma E. 1 upon 2 sigma E, right? And this is what? Sigma E means over the volume, right? And this is potential, work potential is due to the deformation. Ut is deformation at any vector u, we can say, right? So it's a F body load, volume, right? Minus or plus depend on the directions of the loading, right? So we say just plus and totally we can minus, right? So when work done on the system, when work take from the system, so accordingly we can take plus minus. I'm just making all summation. So here you can make ut means transpose this one like this. This is a u, ut means this one, right? Ut traction ds, area of A, right? So area of volume, this is area. Point load plus ut pi, right? 1 to n, point 1 to n, summation. Or either you can make like this, from I is equal to 1 to n, okay? So this is the way we are summing all the forces is work potential. Are the forces work potential? Means there are two things on the system. If you see, if there is board, I can write. So there is two things on the system. See, this is the body. We started, right? We are applying the load. We are just assuming all the load is there, all the stress is there, strain is there. But suppose only one load you are applying, right? So what happen here? It will give you what? Loading system inside. So inside that stress will create it, right? Stress will create it. So it's an internal phenomena. Stress is what? Nothing but internal characteristics. This is internal phenomena. So that's why strain energy is the internal concept of the body, resistance of the body, which is stored inside the body when you apply the work on that, right? And what you work apply, it will be the minus of that, right? Actually, it will be the, because you are applying it, so it will be the minus of that. So it will be stress and strain, it will be like this, okay? And this work you are applying F, this will be like this, because you are applying, you are taking, right? So this will be minus part. So like this. So summation of this total will be 0, should be 0. So what we do now, see, now everything is in their U terms, U. Displacement, displacement, displacement. See here, everything's here. Displacement, 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 displacement. This also 1 upon 2 sigma E, displacement, displacement, rated. So finally, this function, potential energy is a function of displacement, U, right? So now when finite elements solve each element, this displacement is equal to 0 equation. We assume in the ray rates method what we do, A0 plus A1x plus A2x square, assume for the 1D element, something like that we assume. So we assume the differentiation of that is equal to 0, right? Something like that we assume. So when it makes 0, we calculate the value of x. So same here, when we make it 0 integrations, twice the integration is 0, we can get the value of u. That value of u, first we calculate the value of u with the minimum potential energy. So this will give you the value of u. Then from here value of u, we can get what? So this is the process now, bottom top process. Bottom top process is what? You will get the value of u from the minimization of energy, potential energy. So when you work for the finite elements, you got the first deformation. Then from the u, you got epsilon, right? Strain. Then from the strain, you got the stress. And it is correlated to each other, right? We checked it, right? By the Hooke's law and something like that, by the deformation law. So you got the deformation, strain, and stress. Finally, you got the stress result. And those are the needed to design purpose. Because when you have some structure, those has a strength, right? And strength is nothing but maximum stress, right? When you have some structure in the bridges or in the some machines, those have a strength, right? Property, this is some property, mechanical property, right? So you know the strength from the data sheet, right? And this stress up to the maximum burn is the strength, right? So we have to make sure for the proper design, this calculated stress should be the less than the strength, right? So that will be the under the working limit, right? That we go from there, we reach to the factor of safety. From there we reach the factor of safety. Like our calculated stress, how much below the strength? 2 times or 3 times. For the brittle material, we need approx 3 times because they have a sudden failure. So we need approx factor of safety between 2 to 3 for the brittle material. When we design the brittle material, we need factor of safety minimum range of 2 to 3. But when we design of ductile material, because those have ductility, right? Those have ductility. So we can go with the 1 to 2 factor of safety for ductile one, right? So this is the way to calculate and design the things by a FEM, right? And why we choose FEM? It's nothing but virtual of experimentation. Because experimentation is the expensive setups. If something is broken, sensor is broken, because in experiment when you do things, you have to test like this, right? Ultimately experiment does also like this. When this is the system, right? This is the, you make like this, right? Something like, you made like this bar. Like this testing, right? Suppose you are doing tensile testing to calculate the some stress and the properties, right? So when you make the testing, it has machines, right? It has machines. So machines have setups proper, and this is expensive. Those have sensors. Those are very expensive, right? Those are very expensive. So sensors can be broke, and you have to each time purchase, right? So that's why we reach to the finite element, one time purchase and license. Each and every year you can renew the license, and it can solve your many problems. It is the virtue of experiment, we can say. We are setting the model which is replicate the experimental things by a simulations environment, and you do not need to worry about the machines and those kind of things, and you can do it this way, right? So this is the efficient way and the less time consuming way to do work, and you can develop the setup and to give to someone, he or she can use for their purpose. Getting the point? So ultimately our design to calculate the stress, and those stress give us the design purpose. Either we are range in the failure limit or not. If we are in the range of failure limit, then we can say we have to change something in the analysis, right? Change the thickness, change the area, because those are a concept of making the stress lesser, right? So we can make design of like that. Then we think, oh, our stress is, this is the failure strength, failure limit, our stress is now coming under to the 2 times less than that, right? So then we can choose, okay, this model is safe, and now we can go ahead for the manufacturing, because manufacturing again is expensive. When we validate our design under the loading conditions by the simulation software, then we can say this design is validate to the manufacturing, because again manufacturing is expensive, right? 3D printing, either the molding, either the other things, right? And mainly for the composite material, those are very expensive manufacturing technique. SiC has the high temperature manufacturing, those are very expensive. So for that you can validate first, you see this section is properly valid, you give the 10 mm thickness, okay, perfect 10 mm, we can go for manufacturing of this kind of mold or this kind of seats, okay. But you say no, stress is coming very high, we cannot go 10 mm, we have to reach 15 mm according to this analysis. So we can increase the thickness or increase the length, something like that, right? So finally we can propose the design, this proper design is now valid for the manufacturing, because we are studying the composite one, and composite manufacturing is very expensive, right? Like NITE method and other methods for SiC one, for polymer one, those are very expensive and make a sometimes they make a more than $10,000, $15,000 for the one testing and two testings, right? So that's why we go to the simulations and we first fix if it is proper for the design, then only manufacture, else do not waste the money of manufacturing, okay? So that's the way we can understand the finite element by a theoretical things, okay? So I show you the way how it works. Ultimate purpose is to make the massing, and the massing purpose is to solve the nodal equations, elemental equations, and make the purpose potential energy is 0, okay? I hope you understand this. Now we will slowly go ahead of the things which we have in the, this is the theoretical part, how it works, right? But we will go slowly the things how software deal. Then we will see the demonstration in the abacus properly. I will show you one composite, laminate, something like that, and properly I will show you. After that, I will show you the micromechanics. This is a macro mechanical model, right? Macro mechanical model. Macro model means 100 meter, 200 meter, 1000 meter. But when you work on composite, there are the fibers and matrix. Okay, as you see in the professor's lecture, fibers and matrix. So we have to see inside the fiber and matrix what is the damage when under the load, right? What is the damage and what is the stress, right? We have to see. That times we need the micromechanics analysis. I will show you just a glimpse, say what is that, rather than not fully one, but I will just show you the glimpse, say why micromechanics is necessary, because when we show the macro one, it's just a full part. You cannot see fiber and matrix in composite, right? Here maybe some fibers and matrix composite, but you cannot see the concrete one, the cement one is composite, right? Concrete composite, concrete plus cement. You cannot see concrete in this, you will analyze the full one, right? But when you go to micro one or meso one, micro one means micrometer, right? It's a meter one, it's a micrometer one and mm one. So when you see the micro level, you can see the fiber matrix behavior for stress. How much fiber is veering, how much matrix is veering, kind of this. So this is just a way I will show you later on, just normally how it correlated and how these things in the slides, not much details, just glimpse only. But definitely we will see lamina analysis on abacus. Loading something, any loading, I will create any random model and I will show how to create the composite laminate or something like that, and like bending, something like that in the abacus, how to create, right? Continuum cell, conventional cell, those kind of things we can understand by the abacus, okay? So these are the things. Now we will go to the software one, okay? Slowly. So next one is different elements. I showed you elements, massing is very important. So for the solid element, we have a hexagonal element, tetragonal element. For the cell element, we have a cell, the continuum cell, conventional cell. These are for composite I am telling, right? Because this is composite lecture. Rigid element we have, the rigid one means when we have a impact testing of composite, then we don't need the analysis of element. Rigid one is a Young's modulus is very high, right? That means we are not taking the part of that model or the rigid material into the calculation. Just it is the process for the other part. It's just impacting or the like holding the part, right? Like that. But we are not analyzing stress on that part. Means those parts are not under the design consideration. That is for the supporting one, either something like that, right? So different kind of elements we have. Membrane element is for the curvature one. Like when we have a large curvatures and long thin film, then we use the membrane element, right? You can say plane strain kind of things, okay? So these are different elements. We have plane stress element, many elements, you can understand those things. And I just show the few elements, right? Now I will show you the abacus demonstration. So I don't include here, I will just directly open the software and will show you, okay. So I think here is the software Abacus. Okay, Abacus, wait, Abacus CAE, I think I have to type. I will type CAE, Abacus CAE, okay. So I will show you the demonstration. For that we have to choose explicit analysis, implicit analysis, structure analysis, thermal analysis. We have to choose first. Permission denied. Why is denied? Wait, I will open from here maybe. Run as administrator. Wait, is working? Yes. It's working. You cancelled? It was working. Okay. Thank you. So you have 1023 license. Okay, that's great. Okay, so see there. This is the basic version, I think. So that's why only electromagnetic model and standard explicit and implicit model. This is a structural model, right? A structural model, electromagnetic model. There is one more model. If there's extensive version, the heat transfer model also there. Eventually we can do in this also, but maybe we can add here as well. Also multi-body model also, because Abacus is a vast field, right? So vast field. So we have many things there, but we will go with standard explicit and implicit model. And the things behind the explicit implicit one, maybe I covered here. This slide's missed, I think, right? Yeah. So in the analysis, we have a different kind of analysis: structure analysis, flow analysis, heat transfer analysis, electromagnetic analysis, acoustic analysis, biomedical analysis. Depend on the your field, whatever you are working. So COMSOL, MATLAB, Abacus, ANSYS, those have many modules, many tools. You have to choose your domain and work on that, right? Suppose you are a structural expert, but you can use fluid flow intermediate and beginner level. Heat transfer also you can use intermediate, but you have to become one of the expert of that. Then you can say I am the proper CAE engineer, right? If you have one of them expert, then it's like fine. If you are two of them, then it's very fine, right? So this is just a few fields I mentioned. There are many more fields, right? You can do many things in the FEA. You can see the ANSYS or Abacus things. There are many versions you can analyze. These are a few important ones. Those have a recruitment in the industries areas, right? Those have a recruitment industry areas. So like appliances, you have to check the appliances for the heat transfer, fluid flow, like LG appliances, Samsung appliances. Those are the need in the industry right now in the South Korea. Also India, Samsung appliance, you can see they clearly indicate the vacancy of the HVAC analysis, right? So those kind of things working well. So now analysis in this domain, these are the applications. Here analysis retain the linear analysis, non-linear analysis, static analysis, dynamic analysis, steady analysis, transient. What is linear analysis? The linear means under the linearity means minimum deformation. Linearity means just a proper linear way following the Hooke's law properly. Non-linear way means it can be the non-linearity of contact, it can be non-linearity of geometry, it can be non-linearity of material, anything can be a non-linear, right? Static means time domain, static means just a steady state, right? Means this is just a steady state, no moving, like no moving, just a static, no move, right? Then dynamic means moving one, steady means time, no time consideration, transient means time consideration. And here we can include one more, implicit one and explicit one. Implicit one means we are assuming the reversal of matrix, right? Ultimately this is the way, right? F is equal to KU, stiffness matrix and the deformation, right? So this is what F K inverse, right? And U. So inversion, right? So implicit one, what happen? Every time each have inversion matrix, right? Inversion of matrix. And we have a time we can take a large. We have a time taken the large, and when we use implicit, when velocity generalizes, I am telling in the industry one, 10 meter per second. When the velocity very less than 10 meter per second and the quasi-static one, static one, then we use the implicit analysis. Because implicit analysis, right? Because it takes the many iterations to solve. It takes the iterations and it inverts the full matrix. It inverts the full matrix, right? That's why sometimes when you solve it, it's give the error of singularity. It's when you solve in ANSYS or Abacus, it gives the error of singularity. Why? Because matrix inversion is not possible due to failure of boundary condition, failure of loading condition, something like that, right? Then you reach to the explicit analysis. Explicit analysis what does? It does not inverse full matrix, full of the stiffness matrix. It only inverts the diagonality, right? Only it inverts a lumped mass system. It works on as a lumped mass system. It only inverts a diagonal element. Okay, so it's easier, faster. But in that case, you just need make a time step very less time step, very less time step for the explicit one. Okay. So this is for the drop test, crash test, and kind of what others test, impact test, something like that, right? So when the velocity of the system more than the 10 meter per second, then you can use this one. When velocity is very less, then the implicit one you can use, right? Then it will give you the solutions. Although this is more accurate, this is less accurate, but ultimately you can reach up to the 5% error or 6%. Here you can reach within 1% or 2% error. But this will give you very cannot solve, maybe sometimes cannot also solve drop, crash and impact. In that scenario, you need to reach the explicit one, because in that scenario you have to work with the acceleration, right? Explicit work with the acceleration. Here, no acceleration, right? Here is acceleration included. Getting my point? Here is acceleration included, here no acceleration. So that's why you have to work with this system. This system for explicit analysis and this system for very less velocity static one, implicit one. Okay? It's accurate. But here, ultimately you will not get answer what need the accuracy. You are not getting answer, right? Still you will get some answer with 5-6% error. That's why you choose this one. Okay? I hope you got to this point. So this is the different kind of analysis, and now we understand element. Now let's go to this. So our this thing is also cover implicit, explicit one, right? So what we have to do? See what we studied here. See, you can open any software. You can only open any software. These are the steps only you have to follow. These are the steps you have to follow. You can open the console. You can open the ANSYS. You can open the Abacus. You can open the Nastran. You can open the Adams for multibody. Multibody is different one. There is no stress. There is different things, right? Deformation things only, and acceleration things and velocity things. But whatever softwares you open, the scenario of the system is bottom up approach is this only. Okay. Now see here as well, Abacus, simply. See here, modeling, right? Here you will see this, I open this. Modeling, property, assembly, steps, meshing, load, everything is there. Each and every step what we discussed, right? The property is the stiffness things, right? That means in Hooke's law, sigma is equal to E epsilon, right? So that is E is nothing but the property in the calculation. So you can choose the material, either the either the isotropic material, either the composite material. Here you decide the material, right? If you are choosing composite one, you give the property either transversely isotropic, either orthotropic, either the anisotropic. So there is also you decide the system. If there is only the 5 constant, transversely isotropic, 9 constant, orthotropic, 13 constant, general orthotropic, okay, 21 constant, anisotropic, complete one. So this is very difficult to calculate. That's why we assume sometimes 5 or 9, 5 or 9. So just sometimes, many times we use the carbon fiber, glass fiber, armate fiber, we used transversely isotropic, right? Two plane symmetry, one plane symmetry, then no symmetry, right? Something like that. So based on symmetry, the constants are reduced of the 4th order tensors, right? So we use this one or this one depends on that. We give the properties of the lamina or the engineering constant, okay? That decide the material system of us. Either the isotropic, and isotropic just need 2 things. This and this, Young's modulus, Poisson ratio. But when you have a composite, you have a Ex, Ey, Ez, directional properties, right? Poisson X, Poisson Y, Poisson Z, right? This different. And Sayre X, Gx, Gy, Gz. G is different, right? Sayre modulus, this, each and everything you need for the composite one. Getting the point? Okay. So like that we have to decide. Here we decide what kind of analysis we are doing. Then we decide the assembly system. That means in the ANSYS it is not needed the assembly one, but here in the assembly we reach to the zone of the analysis, module zone. Then we decide the step. Here you can see different analysis system, either the implicit, explicit, dynamic explicit, something like that, quasi-static. Depend on your criteria, depend on your application, you can choose the analysis type here. Then interaction means if there is contact, you can decide the interaction. Load you can decide here, loading and boundary condition. You can mass here, mass means the discretization. Optimize, you can check the optimization, then you submit the job and check the result. Okay, this is the way to do, right? Now let's see the part, just make the one part, that's this one. Okay, so I am just using the any extrusion part. Okay, let's make the continuum cell element. Continuum cell element kind of solid cell element. I mentioned here, maybe I will tell you here. Here I mentioned for the composite one we need the conventional cell element. When we have a conventional cell element, we decide the thickness in the software, we give the each plies thickness. When we have a continuum cell element, it's kind of solid cell element that take the element thickness by the relative scenario. We make the element thickness beside, and according to relative scenario it takes the automatically thickness. So this is a solid cell element and it's a faster than solid element, right? And this is only cell element. So this is the more accurate one in kind of abacus. Okay, SCR8, these element kind of SCR8 element. This is the SCR element. Okay, and the others one is the CDR, something like that, CD30, 20, something like that there is. We will see the different element system. But we are going with continuum cell. Maybe we will create the solid element, then make the layers, and then we will analyze that. Okay. So let's see here. Now we just make the one plate. Normally we will do just cantilever plate analysis, something like that. Okay, let's make this one like this. So I'm don't worry about the dimension and these things, just creating. So just for the understanding purpose. Okay. Okay, there we don't need anything, just create this, and now we need extrusion, so I just give the 10 mm extrusion. Just simply I am creating, right, model part, any model, just we are understanding how to work. This is just created, right? So now I think I created very long. Also we have to understand unit consistency here, because in abacus you do not define the unit system, right? So you have to understand the unit consistency. If dimension is mm, result will be megapascal, right? If dimension is meter, result will be Newton. Kind of things you have to understand the unit consistency system. Ton, Newton, ton, megapascal, mm, something like that, right? Kilogram, Newton, meter. Okay, this is the unit consistency system. If you are putting the meter dimension here, then putting the Young's modulus into the Newton meter square. Okay, and when you are putting the dimension is mm, put the Young's modulus material properties in the megapascal. Okay, this is the, remember here is unit there is no unit consistent, like there is no unit system defined, you have to make the unit consistency by yourself. But in ANSYS it is taken care automatically, because there is unit system, you can put the material properties, make the dimension. If you make the meter, they show the meter dimension, then it will automatically convert, right, in ANSYS. But abacus is a unit consistency, you have to manage meter, Newton, kilometer, right, megapascal, ton, mm, something like that. Okay, and dyne, centimeter, like this. Now what we will do, after this we will decide the property. I think I made more thick, but it's okay, we will just example, right? So just as example, right, not about accuracy and something like that, we just example. Now material properties we can enter from here. We enter from here material properties, okay, create the material. So mechanical, see there is different material. Okay, when you are doing the failure analysis, damage of ductile material, you have to define these things, you have to define the damage one. So you can see damage also here. Whenever you are doing the non-linear analysis, we can see the damage also, right? When we use the brittle material damage, the ductile material damage, you can define the yield stress, ultimate stress. So you can see the damage as well here, failure of elements. Also you can see erosion of the element, that is the later on task, right? But here we are just checking the composite simple analysis, elastic one, right? So we are just doing elastic properties, now not isotropic, we are checking the laminar properties, okay? In the lamina, we are considering it's a lamina one, right? So N1, even suppose we are taking the, anything we can take 200 gigapascal, okay? That's, no, we are taking megapascal, okay? So mm all dimension. So 2000, 200 gigapascal, 200, 2000, right, megapascal. So this is megapascal, let's say E2 is same, 200,000, right, 1 to 3. N1, 2, let's decide this Poisson ratio in 1, 2 direction, 0.328, okay. And Z12, like the shear modulus in the XY direction, let's do it 100,000, okay. And Z13, Z13 we can take again 100,000, is the same, 100,000, and we can take 70,000, okay. So kind of thing we decide 70,000, okay. So we decide this one, and this is just a model, and we can just, because we are choosing only one material, okay. So just normal model we created in the megapascal mm system, okay. Then answer will be megapascal later on. Now we have to decide the section. What we are taking the section? Solid section. Let's create the homogenized section, right? Either you can create the cell, okay, and composite, no, wait, others. First we have to go here, this one, section assignment manager, not this, composite layup, because we are defining composite, right? So we will go here, create, that's a conventional cell and continuum cell, right? So we can define anything. So suppose I define the continuum cell, continue, and we can create the layup, how many layup you want. Previously it was option, see, I will again cancel and see here, create, the option is there, how many initial ply count you want. So we can define the element here, how many layer of element we want to introduce here. Suppose I am meshing this later on, 1, 2, 3, 4, 5, 6, 7, 8, 10 element, right? So each element thickness will be decided later on, right? So accordingly we can decide the continuum cell element. So, and the ply means, suppose I define the 3 ply, suppose this is a 10 mm, so 3.3, 3.3, 3.3, something like that, 3 ply will be decided. Suppose I decided 5 ply, so 2, 2, 2, 2, 2, each ply will be cut out, getting the point? So like this will be done. So we can see the ply stack layup later on. So now I just create the 3 ply, continue, and later on you can do also, suppose reason, let's decide the reason of all, the same, this one, okay, done, okay, all is done. Material, let's see, one simple for each. You can change the material as well for everyone, of 1, 2 ply you can decide here, but we are deciding only one material. Element relative thickness on the element basis, right? So we are just taking the 0.3, 0.3, the length of element divided by thickness of that body, right? 0.3, and the rotation angle, let's decide the 0, 45, 90, right? And the integration point means inside the element, the integration point, right? And we are not choosing any symmetry right now, but let's see later on. First here, and we can see what we decided. We can see here. Where is the, wait, here, parts, we can go from here, go to assembly, wait, go to property only. Here is the mark, here we can see. Where is that question mark? Here is not. Here is the one mark. I want to show you the stacking sequence. Why I cannot see here that mark? This one? Oh wait. Reference point element cells. Here is one mark. This one? No. Wait. Sections. There is one dot mark here, like this. There you can check the stack layout. I don't know why it's not visualized here. Composite, special feature, options. That's, you just can check, right? This is not needed. Maybe later on if you come, I will show you. Apply stack plot option, right? Maybe it will show. No, why it's not that point? Here is some point. Maybe you can see here the one like this dot point. Here we can ask the maybe later on it will show. Let's decide the other things. I will show you, and we can check here, change here from there. We can change here what? Edit. We can make it symmetric. That means you will have a 0, 45, 90, then 90, 45, 0. The 6 ply you have right now, okay. So we can do this one and finish it. Now we can go where? Property. In the property, again we can do here, create, this we already done, right? Homogeneous continue, material 1, okay, dismiss, done, right? And this we don't need because we already created the composite layup, okay. So now we define this one, define section 1, right? Now let's do the assembly. The assembly we just making the part, just making the dependent mass part. So it will be dependent on mass. Independent means the part and mass are different one. So only the based on mass the answer will be calculated. As I told you, the mass will focus on the answer part. Okay. So that's not worry. You can choose a dependent, independent. Answer will be same most of the time. But an explicit maybe can be differentiate. So this one is the okay. Right. Now we will go to the here you can do many operation. Transpose. If there is two body, we can make transverse operation, we can make rotate operation, many operation we can do here. Then we can do the steps. In steps you can see many steps. Here you can see many steps. So heat transfer analysis you can do, diffuse analysis you can do, static general, visco, dynamic, direct cyclic, many you can do, right? We are doing this static general, right? This kind of iterative solver. And we can define the time period. So I will define very less time period. So this is just remember. This is also depend on unit system. So if we are working on megapascal, that means second, 1 second, right? So if we are doing 1 second, so I will make the more less because we don't have much time. So just once, I think 0, 1. We are not worried about the answer. And this is the non-linearity if you want to on or not. So you can think your geometry and model. If you think it's a contact analysis or large deformation analysis, not on the elastic region, then you can on the non-linearity also. Right, incrementations just 100, I will make the 10, okay, very fast. So because our basic, remember here, this is very crucial part, when you are defining time period this, make the step more less, so I will make 0.002, so 5 steps, okay, maximum also 0.005, 2 steps, okay. The minimum, sometimes what happen, error comes, so for that you can make this is as minimum as possible. There is many settings, here also one settings, step settings there, you can make the, sometimes here error comes, what's the name of that error, the incrementation error, something like that, maximum incrementation error, right, something like that error comes, and that time you have to increase the IA value. When I remember that IA value you have to make the 15 or 20, something like that, here is the setting. Then you can explore those settings, just we are doing the simple one right now, okay. So this is the way we create the steps. Now interaction, we have no interactions, because only one part, then we can load. If there is 1 or 2 part, you can define different contacts here. I will show you the contact system. So here is a many contact system, see. So here you can define self contact, means automatic standard contact will be defined. Surface to surface contact you can define, model change contact you can define, that standard explicit co-simulation contact, but I don't explore this one. Pressure penetration, I just define the two most of the time. Surface to surface, self contact, in that they and further they ask node to surface, node to node kind of things, right? So those you can define, and that contact, if there is contact phenomena, that automatically take you to the region of non-linearity, okay. If something contact, then you will automatically reach to the region of non-linearity, okay, because the contact non-linearity is there. Due to you define the friction or frictionless system. Okay, so this is not needed because this is done one part, because we are just checking the non-linearity of cantilever. Okay, now after interaction, we don't need interaction, we can go the loading, and loading you can apply any kind of load, surface load, edge load, gravity load, body load, something different load, right? Substructure load, inertia. But as our we are applying the what we apply, the concentrated force we can apply, right? Load 1, mechanical load, electromechanical load. So I am applying this H, selection of the point. So this is because I have no mouse here, so the circulation is very problematic in this. There is no mouse, but I will try to give the here the set selection of the point. This point, okay, there's control. I can go this point or not, I will not know. This point, select, shift, I think. Here you need to use shift. In ANSYS you need to use the control, in ANSYS you need to use the control, and Abacus you need to use the shift, okay. When you want to choose the multiple point multiple A's, you need to use a shift, an ANSYS, an abacus, and in ANSYS you need to use a control. So you can explore this, right? So we have the 2 point and you apply the load, okay, and you can apply the concentrated load. See the direction, Z direction is third direction, right? So apply the minus 10, and it's a what? Unit is what? We are applying the megapascal second, so unit will be Newton per mm square, right? So it will be Newton, right? So 10 Newton we are applying in this direction, opposite, because this is this direction and we are applying like this, right? So we will apply minus 10, and let's say here is 0, 0, so there is no angular load, right? And you can choose the different kind of way of function and uniform, this will be, and this is also you can choose the amplitude by the time 0, 1, 2 like steps, right? So we have a okay, right? So this load is created. Now if we solve with load only, it will not give you answer because we need to make the fixing also. So because the rotation, I will try to rotate it. There is mouse. I am using this one. Okay, got it. Okay, then we will fix it. Okay, so we can use the fix. Okay, I generally work mouse. Okay, no problem. Okay, got it. Yeah, I will here na. Yeah, this one, correct? Okay. Now we will make the boundary conditions. Okay, so we will make the boundary conditions. Let's make all is symmetric one, means the symmetric boundary condition means this is replicating, right? Like this. Symmetric means this is both side. Symmetric boundary condition means like this. This part is extendable this side also if we apply symmetric and load here, right? So it's like this part, like this. Okay. So we apply the symmetric one here, this one, and let's apply the x direction because this is x direction, right? This is x direction. So let's apply the x direction symmetry. Or we can fix also, but fix is very safe. Symmetry can give error, we don't know because this is random model. So let's fix it, okay. I show you the what symmetry does. Symmetry does is just if you apply a symmetry here, this means it's like this. This is the way. If you apply symmetry here, this become like this. Okay, this is symmetry one. So you fixed it, analyze it, model it. Okay, now what you have to do? Still stacking sequence option is not coming. Maybe the different thing. Okay, I will check the tool. Where is the tool? Work view. Graphic view options, no. I will show you the one setup of the view, rotate, zoom, cyclic, specify, toolbar, got it. Toolbar, we don't have the query, okay. Now I will show you the stacking sequence, okay. So what I want to show you previously, stacking sequence, where is the stacking sequence? Mesh stack orientations. There is no mesh now. After that we can see. Let's go to the property. And now investigate. Now investigate feature and the ply stack plot. Okay, see plotting, no plotting, section assignment, region missing section. I think section assignment is not there. This one is the reason. Done. No visible. Ply stack plot. This one. Okay, this one. See, that I want to show you previously. So this was because I used brother's PC. So his was this was option was none. So see, whatever we defined, this is the way we can see the stack plotting system. So this is symmetric one. Ply 1, 2, 3 and the 3, 2, 1, right? This is symmetric plot system. So like that you can see the stacking way. So that I want to show you previously. What happened? Okay. This one is now. Okay. No. I think this connection problem, right? Okay. So here you can see what plotting system you are giving, right? So this is a composite one. See here the composite. This is the, see the view, 0 degree, see the 0 degree, 45 degree, 90 degree, 90 degree, 45 degree, 0 degree. So you can see the stacking sequence are correct or not. You can change it, if you want here, you can change it, you can visualize it, right? So that's I want to show you. Now we reached where? After loading we reach the massing. Optimization, no optimization, let's reach the mass and I will cancel it, so it will give me the one window. Anything you can do from here, what you can do? This I will maximize for full screen, okay. So you can choose anything, viewport, view, this is like kind of WhatsApp, right, this is a tool. When you understand the concept, you can start tool as much as you use, you will become a familiar, right. Then you can learn something Python, here you can copy paste the Python script, it will work, right. Some things, UDF and kind of things for the heat transfer things. But also here the photon subroutine, I don't know how much time is remaining, but I will show you the fast. So you can install that subroutine, something that is not inside inbuilt model, you can explore by the subroutine as well, right. So this is the way to do. Ultimately you reach to the answer. So what you need whatever you package you are purchasing, it gives you all things. But sometimes happen, it does not gives you things, so you can extra subroutine coded in the Fortran language, that will give you the answer. But sometimes happen when you licensed version, you can take the help from technical assistance. They will do behalf of you. Just so your software gives me this much way only and I need this, your software doesn't have this, right. So you, as a technical expertise, please let me know how to do. They will tell there is subroutine. Then they will tell you how to write something like documentation, they will provide. There is Abacus documentation from help you see. There is Abacus documentation somewhere. Abacus Community Learning Company, something like that. You can contact on help, something like that if you license version. Don't contact when you don't have license version, as they will sue you, right. They will fine you 5 lakh rupees, 6 lakh rupees, 3 lakh rupees. But in India, they do not charge with the student. They know many students are using normal version. So they want to learn students, so that's why they allow, okay. But if you ask, you need to license version. If you are licensed, you can ask, I need this because I pay you, then they will give you direction properly on the Zoom meeting or something like that. When you get the direction, you can start the coding and they can help you maybe at 80%, 70%, 50%, depend on your dealing with them, what subroutine you want. Okay, suppose you are doing drop test or impact test, crash test, for that you need the good subroutine, and they will help you to write down properly with the direction. Either you can write and show to them, they will check, and some error, debugging like that they can do with you. But you have to be the licensed version, or you can take the institute help to make the student's account of the licensed version and take contact to a technical team. ANSYS does that. I don't know, Abacus also does, because they have also selling the license, right? So these things is there. So if you have a proper license, you can take the technical help from Abacus team or ANSYS team or the Composite team. They will definitely help because they are technical engineer and they know how to do these things, right? So you can, because we are just doing for our application. Our purpose is to designing, right? We are engineer, they will show you the solution because they are developer, then we can learn from them and we can use in industry or our academia, right? And we can teach to students, that's the way to do. It's not that in every problem you just go down on the well and just searching something. Try to take the help also sometimes in Abacus ANSYS, that's also best way, right? Okay, now massing, we have a noding thing, see here. This decides the nodes, element, and different kind of elements system we can decide. So nodes dependent instance cannot be assigned by the see here, we have to make the part system, right? So let's see the mass. Okay, so they are making approximate global size 5, so we just make the okay 2, something like that, apply, this size is defined, right? Node is defined means, that means all nodes are defined. Okay, then we can see the massing and we can generate the part massing, right? So mass is done. This is very simple part, so all element is a hexagonal element, most of them, right? As see here 1, 2, 3, 4, 5, this will give you wrong result because only the 5 and we have 6 layers, right? So at least each element, each thickness has a 1, right? So let's go with this, make here, what happened now? Which one, this one? Okay. Okay, working? Okay, so let's define here 6-1, let's define here 6-1, right? So done. Let's define approximate global size element, let's make 1. 6 or more than 6 is okay. Complete mass, okay, how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's make 12, right? So we can decide for the 12 we need by number, right? Let's define the 12. So each thickness has 2 elements, right? Because we have 6 layups. Okay, so we define this one. We can make each layup 4 also, 3 also, like that, right? So this will give us a element. Let's match the part. See, now it's looking okay. Now we can define the element type, right? So we have a continuum cell analysis, right? So let's go the continuum cell one, okay? And choose the second order accuracy, and these things you can choose. If you have a damage analysis, you define the damage system in the properties, then you can use the element deletion, maximum degradation. These things are for the damage analysis, not for normal analysis, right? So we are just continuum cell element, right? You can choose solid cell as well, and you can say the you can choose here explicit element when you have explicit analysis, but we are doing static general analysis, so we don't need the explicit one, and we say the okay. Like element is decided, everything is decided. If also this is chance, we can miss something. When we run, it gives show you the point, that's do this, do that, right? It will show you, then you can do, right? Now you can submit the job and you can analyze it, right? You can create the job, save it, and you can analyze it, and if something error is there, it will show you, right? That you can do. Okay. Now we come to the point, because it will take time to run, and we have just 10 to 15 minutes, so I want to show you a little bit MATLAB things and subroutine part, okay. So but it's just completed all, but if you run, maybe something error will come. So what error will come? Suppose section is not defined, this is not defined. Suppose it say error, section is not defined and this is not defined, then you can go, okay, let's say run it. If run is background, it will be run automatically. Okay, so let's say create the job, continue. Description no general, because if you want subroutine, you have to make subroutine here and add it, right? That will be the best one. So we just create the full analysis, okay, and we can submit the analysis from here. Okay, we can submit data check, we can do here. If something is missing, it will show you. If missing, it will show you. Submit it for analysis. So it's just checking the data if something is missing. So everything is checked. If not missing, it's safe for the analysis, okay, completed successfully. That means everything is properly, okay. If completed successfully, that means there is no error, okay. Now only the error can comes due to the our boundary conditions. Everything set up means check completed. Now you can submit analysis, okay. But if something error, it will show here. This is very like convenient things they talk you. So they talking that standard successfully means there is no error. You can run. If the error is maybe loading error, geometry error, something like that, your modeling error can be, but setup error is no right now, right? So you can run it properly and get the answer. But if something is there, they will say the section error, contact error, boundary error. So you can go again here and you can change the things, right? And you can run it and get the answers. And when you get the answer, you can visualize the stress, strain, and the other things, right? I hope you get it. When you get the answer, you can visualize from here. Visualization, okay? So these are the things. Now let's come to the point. This I showed you. Step to the subroutine. So subroutine needs, the subroutine I told you why subroutine needs, when those the things we have not in the model. When the things those not are in the software itself in the inbuilt, then we need subroutine. Like kind of when we are taking the heat transfer calculation, deflux subroutine needed. When we are doing a welding analysis, we have to need the like dat and bird subroutine. Right now in ANSYS it's automatically updated, newer version, but here I think we have to write the subroutine. Sometimes it is there but not that much accurate. And when we write the filament one, I did in the IDM something like that. So it was when we writing the filament one, that extrusion temperature, so we have to calculate the temperature subroutine by that, because higher temperature, those it cannot cover. So for temperature one, velocity one, when you write the flow system, so UDF, these kind of things you can write here, subroutine. That's called a subroutine. Those are not inbuilt. And also do not worry, if you are the advanced researcher, you can take the help of community. They will help you. If you have a license, you can show the license of university, that we have a license in the university and this is the license name, and this is my license name, and talk to that will help you. If not, insist to help. Say that our research team or the lab team want to ask this because we have purchased from you, right? So they will help you definitely. Not 100%, they will give the direction, 50% they will help, and then you can develop your own. They can give you direction, or you can read the documentation as well. Now many sources are there to read, right? So here you can get the subroutine one. See here, suppose I am creating job 2. See, when you have a subroutine, you can enter here. It's kind of the .f file, photon file, right? You can enter here, search directory, use subroutine. For that, you need to make the so you can add the subroutine here, right? Where is the right input? So when you have a subroutine, you can enter here. Right? Continue this point. General, when you write a .f file, you can make the insert here. But for that file, writing the file is okay. You can write, you can take somewhere. Maybe you can take the help of AI system, ChatGPT and other things, right? But when you write the subroutine, you can take this file .f file here. But before that, you have to set up the system of that subroutine. How to set up the system? What 3 things is needed? Need the Intel compiler, Visual Studio and Abacus, and the compatibility of the system. Abacus compatibility with the Visual Studio with the Intel compiler. Those kind of compatibility is needed. That means the Abacus more than 6.13 version or the 2.18 version, more than that, need a different Visual Studio, right? And below, like before, older version need different Visual Studio, different Intel compiler. So you need to check the software's compatibility with each other. Visual Studio, Intel compiler and the Abacus. So all 3 versions should be properly associated to each other, right? Compatibility should be there. So we need 3 things, right? Configure Abacus to run the and compile them with the purpose Visual Studio, Intel Photon compiler are needed, right? Because the subroutine is nothing but Photon file. So we need a Visual Studio, Intel Photon, and those for we just need the compatibility of that. Like suppose I say I have a 6.15 Abacus or 6.14, then I say for me 2018 or 19 Visual Studio is okay, and for me Intel Photon 2014-15 more than that is okay. Like that we have to understand the compatibility. So in the documentation it is referred. If you have this Abacus, you can go with this compiler of Intel Photon and this compiler of Visual Studio, right? Then you can install those things on your computer, give them permission, give them environmental path. What is the environmental path? You can see here, edit environmental variable. The environmental editor, right? Edit environmental variable. You can give here the path of them, a path of the Visual Studio. Here enter the path, edit. You can add the path of Visual Studio, add the path of Intel compiler, add the path of your Abacus, and then after those all things you can make this whatever I told you. After this whatever I told you, you can go here after compatibility, installation, defining editor, defining the system administration. You can create these things, this one, this file. Then you can make the directory of that file particular way. Sometimes what happen, another directory it will not work, so you can just install the Intel compiler, Microsoft Studio and your Abacus file, whatever ODB file you are working with, you are saving the Abacus file in .odb or .py format, right? And the .f all should be in C drive, the best way if not working other directory, because everything installed in C drive properly. But if other directory also, you can define by edit environmental path this way. I told you this one. Where is that path? I showed you, right? Setting one, edit environmental variable, this one, right? I showed you already. So you can define there both all the things, and you can define a working directory. You can upload your file, the Photon file path, and you can say okay and then can run. So this is the way. And now I will show you the more things about the installation, right, of the subroutine file path. So ensure that you have software installed, Abacus. If you have, that's okay. If you have a more than Abacus 2020 version, Photon version 19 and the Visual Studio 2019 is better compatible, right? So 2022 means approx 6.15 or 6.16 2022, right? So you can define the compatibility of that. Okay, when you check the compatibility, download accordingly only. If you see 2022, if you download Microsoft Studio Visual 2018, that will not work, and you say I have but it's not working. Check the compatibility, install it properly with the administration permission, define the edit environmental variable, then properly check the directory, check the subroutine file and run it, it will run. Okay, check for simple model, then run to the complex one, because when you run for simple model, it will automatically adopt the environment of your computer. then run for complex model. If you directly run for complex, maybe it's difficult to adopt the environment, right? That's why run for one element, two element, then adopt the environment, then run for big model. Okay, so Microsoft Visual Studio, how to install that? You can install the Visual Studio like this way. Microsoft Visual environment and the Photon environment must complete the installation. Visual Studio before the Photon compiler, like that you can install the Visual Studio, right? So maybe if you want, I can provide this PDF so you can follow that. You can install the Intel 1 KPI toolkit all, this one, right? So you can install by this method the Intel KPI, right? Intel API. So you have a Visual Studio Intel 1, then you can install the HPC toolkit, right? That is just a API toolkit with the Intel performer, right? Okay, then after this, once we have a software successfully installed, all installed, right? So maybe your directory is C program 86, C program 86. This is your Intel compiler. This is your Visual Studio. Both are there. Then identify the batch file of this one, right? When you identify the batch file and add environmental variable, right? I showed you the environmental variable. So make this batch file identification. So your environmental variable can edit and can read the vc verself.bat and vers.bat file. When you install all things, Microsoft Visual Studio, Intel compiler, you need to make sure that your add environmental variable has those kind of readability, this one and this one. Either you can add by the environmental edit setting those file there, directory there. Okay, when you add this directory, you will make sure this will be the this system. Now go to the environment system environment and two files sketch path as shown below. You can find serving environment in the window and search bar. So you can make sure that these things will be in your add environmental variable path, right? Like this. See, those paths we have included. Okay. Then next step is to configure abacus.bat file to file shown in the below figure. Now you can just configure this by the calling of this, the echo of set local, and this you can just you are configuring by this. That means you install successfully, you invite the environmental variable, just you are checking, right? So this will your final call, and to make sure very good job and your system will done. You can check the system by abacus information system that will identify the Photon compiler. That means you finally finish the installation things. Okay, you got the subroutine system set up. Now you can just import the directory, import the subroutine.f file. It will be run for you, right? For the job purpose, like for the analysis purpose of the job. Okay. Now I just want to quick glimpse of in the 10-15 minutes I will just show you the MATLAB tool as well, because MATLAB is a students it's a versatilely free version, right? So MATLAB is just a tool. That name is actually MATLAB is a mathematics, right? And abacus is kind of calculator. That's abacus name is kind of matrix. MATLAB is kind of mathematic tool. Okay. So this is just what PDE tool in MATLAB. If you search PDE tool in command bar, just type this one. This is the function tool, right? So it will open the window of this GUI. Here you can make simple static structural, right? Structural, heat transfer, electromagnetic, simple analysis, not complex one, right? Simple GUI analysis based, right? Simple analysis you can do in the MATLAB for the student purpose, for the assignment purpose, simple one, not that big much. And the CFD tool we have in the MATLAB, they have, not we. They have simple CFD toolbox. There you can analyze the flow analysis, right? They have a magnetic box. There you can analyze the magnetic analysis. So the toolbox have everything. Just install that toolbox, run it, and then follow that portion of the command. I will show you only the PDE toolbox, that is partial differential equation for the FEA. This is for the FEA. You have a magnetic toolbox for the magnetic field analysis. You have a CFD toolbar for the CFD analysis. Different toolbar are there in the MATLAB itself. You can just install that toolbar and run it. Run the app. This is app like a WhatsApp app, Kakao app, like this, right? So you have a different app. Just open that app and work on that. That's simple for simple analysis, right? Not for big deal. Like some cantilever beam analysis, some tension analysis, like simple analysis. Okay. Not big. For the big one, you have to go COMSOL, ANSYS, abacus, Nastran, these things, MSc, sorry. So these are the way. Finite element toolbox for Sachdeva. So now you have to go what? Open the MATLAB, open the apps, open the app. Then you will find out the here you will find out the PDE toolbar. When you go to app, you can find out the PDE toolbar. Different toolbar is there. If there is MATLAB, I can show you. Where this one? I will show you here. There is no internet. So when you open the MATLAB, it looks like this app, you can show it, right? And when you solve the MATLAB setup, there is different thing. Create the PDE, that's create the model. This is a function, right? In the MATLAB inbuilt function. When you write in the MATLAB command bar, create PDE, that will create the model. Structural property is a function to assign the structural property. Structural damping, this is directly the function formula. Directly function, you just write the solve, model name, it will solve. Structure IC, structure BC is a command way to solve in the MATLAB, right? You have to just write the function, it will give you the answer. Okay? Write the function, it will give answer, you can just read it, right? Normally. And when you go solution 1, evaluate stress a function, give the stress solution. Evaluate strain will give you the strain solution. Evaluate one basis stress will give you the one basis solution. Reactions will give you reaction solution. So after these function will give you the model setup and meshing setup and analysis setup. This is a function in MATLAB you can use directly for this purpose. Okay. So these are the function you can use directly for this setup. Okay. And these are the function you can use directly for this answer setup. If you can open the internet, I can show you how you can get this different tool app. Internet is there. Available Wi-Fi, NITJ Wi-Fi, connect automatically, connect. Connect it. No? Did you guys boring or it's okay? Understanding something? Enjoying? You understand? Important, you are the important person for me. You also important. Okay, so MATLAB online. Okay, this one. Never. Okay, open MATLAB online. So see here, this is just different thing I just calculated. This is not needed. Actually, this is my online MATLAB thing. So just I want to show here. See the here different app. So we can do what? Open this. You can see the PDE tool right here. This is the apps, right? Kind of WhatsApp, your Snapchat, this kind of things, right? This is a PDE modular. Here you can see. When you launch the PDE modular, here you can see the partial differential equation solution or the simple analysis, right? The optimization things, signal things where there is a big browse area. Right? Also, you can type here. Also, if you have not this much patience to go to app, just cancel it. You can type here PDE tool. This one, right? So enter it. I hope it will open the PDE tool. See this one, okay. So here the see same thing. What we mentioned into here, what we see. Okay. So what we see here, what we see the system here, same thing we see in Abacus. Remember, you can see same thing in the ANSYS, you can see same thing in the scenario in console, and now you see in the same thing at here. Where is online? This one, right? You see here also same thing. geometry, boundary condition, differential equation solving and something like that, right? Everything is same everywhere, right? Right. So we will see here we have to make a drawing the geometry. You can drawing. I am touching this. Okay. I will stand here then. Okay, sorry. I will stand here. Okay, see, drawing, you can create the simple drawing. See, this is not very complex one. Very simple one, right? 2D model, plane stress model, plane strain, very simple one. Then you can apply the boundary condition, very simple boundary condition, right? You define the subdomain level, partial differential equation, you can define the partial differential mode, then you define the meshes, very simple meshes there are only the triangular meshes, the quadrilateral meshes, right? Just see, this is only the triangular and quadrilateral, right? And this is the PDE coefficient, this is the boundary conditions, this simple way and you can run it. And you can define the analysis type from here, static structure, plane stress, plane strain, electromagnetic, magnetostatic, heat transfer. So this kind of system you can do very simple way, right? From here you can choose as well this one, different app you can choose, right? Different app. Also you can do these things also, what I mentioned here, that the GUI, the simple way, right? You can choose this one as well, where the system I showed you, the command system, right? The command system, this one. I will show you the code also this way, right? I will show as I open the online, so I can show you the code system. So I created the PDE tool. So you can see the PDE one. If I just say study transient. So you can see the create model and these things is there. Here is there, right? This I do not touch. I am very far. See here, this see directly it's using, right? See, A is boundary conditions, generate mesh. See, this is a function. Generate mesh is function. Writing the spelling is given become a function, right? See, this is a function. Generate mesh, age load, dot age BC, title, PDE plot. This is the diagram you are making, right? And material properties dot my model means you are assigning. See, this is the complete model. First model you define, right? So you are defining the model. This one. So this become, see, this become your like analysis domain, right? Reason, and you are defining the geometry from that, right? R1, R2. Then you are defining the figure of geometry. Then you have a model. Model you are creating FEM model, analysis type, thermal transient, not the static structure. Whatever you will write, it will automatically pick up that model, right? The geometry condition. Then that model now taking the boundary conditions. At age, temperature this one. At age 1, temperature this one. This was very simple model, because for big model you cannot define each age as each node, right? This very simple model are the triangular, rectangle model, or just kind of a cubic model. So you know the every age and this age and the nodes, so you can define this. So model defined, then model at age. So you are going to university gate, then the mechanical campus, same. Model going to age, then model to age, then age to 6 number age, okay? Then you are creating the temperature, then same like this. Then material properties you are defined the thermal conductivity and these things figure, then you generate the PDE mesh. This is I told you, this one, right? Function. So this function, these function use the same way, right? This function use in the same way we used already here. I showed you. The same way directly write the function name and the function works for that and you can get the answer. Okay? So this is the way you can do by the command one, but for that okay, so for that this is just plotting, right? MATLAB plotting you knows already, right? Also for the literature publication you should use the MATLAB or Python plotting. Excel plotting is not good. Python plotting is good, either MATLAB plotting. Just you can find the code structure from the any AI tool, or you can create by your own. Just replace your data and use it, right? So plot will be good. The researcher plot is good, right, for the general article. A good plot can be created by MATLAB. The engineering plot, you can create by MATLAB by the Python. Python plot is also well. So in the Python you can use the plotting tool, the PY tool, something like that, the PY tool and the shape figure, something like that there is in Python tool also. And here is the PD plot. Directly plot command is there. The cubic plot command is there, so you can use those plotting things, right, at here. So this is the way to do the MATLAB by command, and I show you the GUI as well from here. Here you can type the PDE tool, it will open the GUI as well, right. So we have understood the both things, and for the creation in MATLAB, the normal command way, you can read the different command system, and there is the library of the command. Actually this is not a command, it is a function. It's a function, right. Everything in the mathematics is a function, right, works as a way of function. In the physics everything is a function. So same way you have a storage of the things. Create PDE means storage of the many commands inside that create the according to dimension, create the model. So those have different functions that create the different things. This is the way. So you can define by the coding system as well. 10 minutes more. Okay, so and this is the this setup function, please remember, this is the setup function, this is setup function, this is the solution at nodal location, right, this gives a solution at nodal, right, this is the function to get the interpolate the function, means node solution we want the inside the node, right, extrapolate outside the node. This is the visualization function, PDE plot 3D, PDE mesh. So the command is for the MATLAB. When you give this function command, that give you the visualization in the MATLAB only, not the GUI one, right. Although GUI use the same thing, that becomes a button, that PDE plot become a button at there, this plotting, right. So the function become a button, they using as an app. Okay, this is the same thing using by the command line and using by the app system. The model properties, you can define the structure boundary condition, damping boundary condition, loading condition. This is the way. Solving, you can use a solve, FEM time if you have time, right, transient one, no time, just FEM. Model name, that means model name. As there we define model name as a model. You can define model name as job 1, job 2, right. You can define model name as your name, right. BR Ambedkar, you can write the model name, right. So you can define anything. A time list, you can define the frequency list, you can define the range, everything you can define there. But this is very simple for the simple problem. For the complex problem, just use abacus, ANSYS, COMSOL, these things. Multiphysics COMSOL is better, multiphysics ANSYS is better. For the structural and the explicit one, this one is better, abacus is better, okay. For the structural, for the accuracy purpose, static or the implicit explicit, abacus is best. For the CFD tool, you can use the ANSYS CFD, or for the more complex LS Dyna kind of, you can use ANSYS. For the multiphysics, you can use the COMSOL. Multiphysics ANSYS is also okay. Open the, okay. So you got this, right? And here, okay. So now, after reaching this, we understand the solving system and get the answers, right? This is the app tool, right? Open the PDE tool, I showed you, this will open like this, UI view, and you can create the simple geometry and define the boundary, define the material properties, right? And then define the meshing system and then solve it. It will give the answers like epsilon and something like that, the color 3D view, something. From here you can change the visual view system, and then you can read more about the problem by this link. If you open the link, the bracket analysis problem is there by the MATLAB FEM, then you can open and check it, right? And again MATLAB has other things, right? For the control and design purpose, the Simscape, Simulink is there. Simulink is for the controlling and the network marketing things, like for the controller and these things, you can make the Simulink model, control designs and Simscape. So Simulink open by Simulink, just type in the command line, Simscape type for the multi-body one, and the machine learning box is there, statistics box is there. So MATLAB you have many tools to use for the normal analysis, composite check, node analysis, these kind of things, okay. And these are the library to work with the different kind of analysis. Battery system nowadays in the convergence things, and the future industry of the battery is going on, right, EV system. So you can work with this. If you learn, maybe some industry has requirement of the battery analysis, package analysis, so you can go, you can say I have a tool batteries I know in the MATLAB and I can solve the COMSOL, the multiphysics of batteries, so they can consider something like that you can do, right, okay. And for that, after that, you have the suggested book of MATLAB, you can use those kind of things for MATLAB, and for the Abacus you have a documentation and the Abacus help. Okay. Abacus help, you have a documentation, from there you can get, but click on here when you have the license one, okay, else they will detect you. Student as okay, student license is okay, there is no problem, right. So these are the way. Now I just sign out, okay, but that is very important. Now what we do, what we have to understand, this is just a suggestion of books, you can read or you can go by online sources, there are many things, or the MATLAB documentation are there. One more thing, I want to show you for the composite one. So as you know, the composite, we have the because we have remaining 5-6 minutes. So as we know, after this one more lecture is there or finish? Finish? Okay, then we will finish in 5 minutes. Okay, see. So we have the system of this thing. Like, so you see the car, right? Suppose the car body is become a carbon fiber, right? We don't know it's a fake composite, flake composite, particulate composite, whisker, braided, bovine or laminated. We don't know, right? So that's why I say this is a macro model, right? Inside that there is the meso and micro model, right? This is the. So when we do the multi-scale analysis and modeling, we have to check if there is something here or not. Everything is well inside it, right? Crack propagation start from the because crack propagation start from the micro level, right? So we have to check in fiber and matrix everything well or not. So that's why sometimes what we do when we find the mechanical properties, when we find the failure analysis, we do from the micro, meso and macro, right? Like this way. Micro scale, fiber and matrix. Meso scale, come to the bundle of the fiber. Then macro scale, the big structure, right? So we check the result at here, result at here, result at here, and these all are connected by the potential energies because the system is together, like continuous, like discrete system, the inbuilt to the connected between both of them. So we assume when we analyze, we assume that when we are working with micro analysis, we use the RBE system, representative volume element, that RBE, that we assume the fiber and matrix together makes the many times of gathering, like legs of fiber and matrix has gathered to make a one big structure, right? So we say that's a repetition of a structure. So if we analyze a simple one with the periodic boundary condition, it says it has what impact can go to the others also, right? So that's why we go to the micro analysis, then we understand this system, then we check the loss of energy between micro to macro is the 0, then we work for the macro analysis system. This result we input into the macro one, right? Either we do another system, either we run the macro analysis, right? We get the stress, macro one, right? Suppose 2 more minutes. Suppose we are doing suppose you develop this system, right? You develop this system, kind of flex system, right? So you made this with the carbon fiber, this structure, with this structure, right? You made the 0, 45, 90 structure. Okay. Now you are analyzing, but when you see this will not look inside like this, right? You run this, you got the stress 90 megapascal, suppose, at this point, right? You know this is the complex part, right? So what you do, this part, you know how the distribution is there. Just take this part and take this part here, right? So you know the variation of the fiber and matrix at there, right? And then you do what? This deformation. From here you have a deformation also, right? Deformation is strain. Apply this deformation, calculate deformation at here, this part, small part. Then you get the result at the fiber and matrix. How it behave? Maybe this stress now it made 90. Maybe this is 120, inside is more, right? So like that you can understand the inside one, macro to micro. And when we are checking this deformation to here, we are thinking there is no energy loss between the connection, right? This is also assumption with the micro to macro and micro to meso to macro, okay? So this is a multi-scale point of view. I just show the quick glimpse of you, right? So this is a way to work with composite, like a lamina composite, particulate composite, whisker composite, woven composite, braided composite. Nowadays, The woven and braided is the key structure because nowadays woven and braided composite is the key structure because this is started using in the turbine blade system, and this is also started using the complex wind system like the wing system. So because they can negotiate the bidirectional way, right? Bidirectional stress, so they can compensate to each other. So this is the advanced composite, right? The geometrical way, and this is the what I am showing here of the professor shows many classification and many things. What I am showing here now, you just these are the geometrical classification, okay? These are the fiber orientation based classification, okay? The composite many classification, PMA, MMA, like polymer matrix, metal matrix, ceramic matrix, those different one, right? Based on the matrix, based on the polymer, we have a different classification. That's I showed you based on the geometry, because when we analyze the composite, our FEA works with the modeling, massing, analysis, boundary condition. So modeling means based on geometry. So that's why I am showing you the geometry consideration, okay? So now you understand the multi-scale way, just I show you the approach only, not much, okay? Okay, so now you understand this, and I showed you abacus and these things. Now let's we summarize. So I will just ask you what you understand, then you can ask me the question. Let's we summarize the today's things, what we get in the 2 minutes we will summarize, okay? What we got in the 3 hour. So let's summarize one by one. Any 3-4 person can say, so we can summarize it, then we can finish the class, and then you can ask the question. Let's summarize. So what we covered? Let's summarize what we covered in 3 hours. Okay, developing the abacus model. Developing the model, right? Abacus model. Second, any other? API background. Okay, the theory background. Okay, theory calculations. And what others? Massing part, right? Sir, any input from you?
Use of MATLAB.
Use of MATLAB, okay. Okay, then what others, sir?
Using PD tools.
PD tools, okay. PD tools. Okay, next, let's create 10 only or 8 only. Brother, any input from you so other can, maybe they do not listen, you listen something. Maybe I forgot something, then you can tell. The multi-scale, okay, multi-scale. Multi-scale understanding, only the understanding, right? Then you? The MATLAB one already covered, okay? The PD tool and MATLAB one, okay. Any other input? Different tools of MATLAB, right? Different tools and functions of MATLAB, right? Tools and functions, right? Subroutine, right? So we covered today like FEA background, structure, how to work in abacus, subroutine installation, subroutine background, right? Then we covered the MATLAB, PD tool, and how to work the functions of MATLAB, then multi-scale modeling. So those are the things we covered today, and I hope you understand the things, and you can ask me the rated questions. If I can answer well, that's okay. If something is there, I will help you. That's it. Okay, thank you. So if you have a question, please ask, then we can discuss, or just discussion is okay, as you want for the few minutes. So. Any discussion needed?
Explicit model, you said that the velocity should be greater than 10 meter per second.
Yeah.
What velocity means what type of velocity you discuss?
The velocity means the when you see the drop testing, right? The system should have a higher the movement, right? Suppose I am static, right? Suppose this is the model, right? You are analyzing stress is this point, right? So you know the notch has high stress, but this is static model. I am analyzing this, so it's static. Implicit I can do, right? But this is moving like this, right? So I will do this with explicit one, because consideration of velocity and acceleration will be explicitly covered well. Although the accuracy is little less, but this cannot be solved by implicit one, because if it's solved by implicit one, that will take too long time, and maybe can give the error, because the inverse of matrix of whole matrix and the one element, right, here are many elements, right, the moving element, this explicit works like this, right, this way. So F is equal to ma, right, system. So involve of acceleration is there due to higher velocity. So when you involve the matrix inversion, here will be more complex, right, because of the nodal system, many nodal system and movement of the nodal. But implicit one, static one, no much difference, quasi-static one, simple one. So the inverse of matrix is possible very easily, right? So this is the way. So that's why I said the velocity is less, you implicit more, then go to explicit. So the explicit give you the answer, although 4 to 5%, 6% error, but at least you reach somewhere, right? So rather than nothing answer, you can have some answer. Okay? No more question? Any question? Any question? Vic?
Suppose we are 3D printing, suppose I am taking an example. We have project of printing continuous fiber with the resin. So how we take that model with the means simulation? How can we take?
So you are in the manufacturing model, or the after manufacturing you want to check the residual stress or the analysis? So you mean after the making part, you want to check the residual stress of the making part analysis or the manufacturing process analysis?
No, sir. The actual means suppose we are manufacturing materials with the continuous fiber and the resin.
So you have the fibers like this and the resin inside, right?
So how that model is means similar to the model we are means taking in the simulation.
You want to simulate?
What you want to simulate the manufacturing process, or you want to check the stress of the manufacturing? So
Manufacturing product
stress you want to check, right? So you have the 3D printing machines, the filament based or the different one, laser printing? Resin 3D printing. So you have the printed part, right? Then you want to check the printed part stress, right? So you have the design of the part, right? Stress of the part. So you know how it's printed. You know its printed, how it's printed, right? And you know the layer background, right? 0, 0, 0 or 0, 90, 45, you know these things, everything, right? So you can make the one big part, macro part, analyze it, check the stress of it, and make the small micro part, because it's a revision, right? You know this part is similar at this here, this part, so it's, you can take RBE, this is small RBE, right? Take this one out, make the small part. Like this is in micrometer, this is in micrometer, this is in meters, right? Big part. You are printing in meters? 2 meter, 1 meter, something like that. Then mm, centimeter. So this is also meter. Let's suppose 100 centimeter, 40 centimeter less 0.5 meter, right? Something like that, right? Right. So this is meter, right? But micrometer if you go, so you can go to 10 micrometer, less part. So you can model this one, analyze this, check the deformation here, then check here. And you want to calculate the what? Mechanical properties of this? You want to calculate? You want the E1, E2 because you don't know. Then you can do what? I will suggest you. Then you can do what? First create this one. First create this one, a small part like this. So this is your fiber. This is your fiber, and this is matrix. So for that you have to know the fiber volume fraction. Fiber volume fraction. Okay. You have to know fiber volume fraction. You can create the fiber. This is a one directional fiber, right? Unidirectional you are creating. So this is your fiber. Just create the outside one thing. So this will white background your matrix. White background. White. Where's the pen? Okay, so white background your matrix, and this is your fiber, right? Just create like this. Now you have to do what? You are finding mechanical properties, right? That means E1, E2, epsilon 1, epsilon 2, epsilon 3, something like that you are finding, right? Right? So if you make a 2D, that can find on to E1, E2. But if you make it 3D like this, it can find this like this, right? Fiber matrix, right? It can find the E1, E2, E3, Z12, Z23, Z13, and nu12, nu23, nu13, right? So for that you have to apply, suppose you are applying the load here, one directional load. So this is only X, suppose this is X direction, right? X direction, Y direction, Z direction, right? So suppose you are applying the X direction load, make sure this is only the X direction deformation. This direction, this direction, this direction deformation 0. How will you make 0? Make the periodic boundary condition here, periodic boundary condition here, periodic boundary condition here, periodic here, right? Only load this will give the displacement of this. So that means this deformation only give you the stress in this direction, right? That means stress upon strain will become your E, even. So sigma 1 only you get. Remember, you have no stress here, no stress here, no stress here, no stress here. Apply the boundary condition like that. You can read the article. I have done this, or any other also done this. There is article. Just create the RBE first. You are calculating mechanical properties, right? You are evaluating mechanical properties. Just create RBE. Apply the load or deformation like that. You just getting the sigma 1 and E1, not sigma 2, not sigma 3. There is no sigma 2, sigma 3, no tau 1, 2, no tau 2, 3. If there is, that means near to 0, because there is definitely, but near to 0. Okay. Assume that this is near to 0. If all 0, just sigma 1 E1, divide that will give you E1, epsilon 1. That means you got the Young's modulus in this direction. So fiber unidirectional, you got the E1. Now you need E2. Apply the load here and make sure only give the sigma 2 and E2. Sigma 2 upon E2, E2, right? And when you are applying a shear, check the which plane you are applying a shear, like this. So you have to make the, also when you do composite analysis, the testing, you make the fixture like this. When you apply the load this direction, it will create the deformation this direction, stop the this direction deformation. So this, then when you do the testing also, fixture does this like only. So this we are making the virtue of experiment like this, okay. So do this, you will get the E1, E2, E3, E4, E1, E2, E3, G12, G23, G13, nu 1, 2, nu 2, 3, nu 1, 3, or the transverse isotropic, then E1, E2 is equal to E3, G12, G23 equal to G13, and nu 1, 2, nu 2, 3 equal to nu 1, 3, right. So you got the 5 models, right. Then apply the full model. Now full just make like this only. Just if you create this model only. Now apply this to here, this directly. You got the mechanical properties from here, micromechanical. Apply this property, continuum model directly. Now you don't need to apply the ply here. You don't need to model like this now, because you created the here, right? Because this is the repetition of this, right? This repetition will create this, right? So you got the properties from here. Just apply these property here directly. Now mass it simply, and this is homogenized model. Here you do not need to make the composite model. Here you need to make the homogenized model, isotropic model. Not isotropic, anisotropic model, the engineering constant model, but just no ply needed. Here no ply needed, no fiber needed, no matrix needed. Just normal model, mass it, apply those property here. Now this result will give you the consideration of your matrix and fiber. But when you create this, remember the fiber volume fraction, okay? Getting my point? So understand a little bit RBE, apply the RBE things, get the mechanical properties, apply the mechanical properties here, failure strength here. After that you get the result from here, the design result or the stress result and whatever is coming from your design part, you will get here, the macro part. And it is not a composite one, homogeneous part. This is a homogenization, this is a homogeneous. It's a multi-scale modeling, micro to macro, okay? This is the way to do. And opposite way, reverse way, analysis here, get the result here by the deformation, right? This is the reverse one, right? Okay. Getting the point? Anything? You understood, right?
What will be the size of RBE?
RBE size should be by the depend on the your part, right? By like you can choose the 100 micrometer to 100 micrometer to 100 micrometer. Like if suppose you know the manufacturing part, right? Process. You think if the repetition of the part after the length of the this much gap is 100 micrometer or 1 mm or 5 mm. So as much as long you can put, that will give you the as accurate result, right? Understanding you got. Suppose you are picking the 1 mm RBE, but you think the 2 mm can cover the more proper repetition. So choose the 2 mm. Okay, but you think no, only 100 mm, 100 micrometer RBE can cover the repetition. So you think your manufactured part is the repetition of how much dimension? That's the RBE, right? Representative volume element. So if you see your macro part is the meso part is the repetition of 10 micrometer. Each 10 micrometer is repeated, so you will create 10 micrometer. If you see by the image, if you see the big part is the repetition of 2 mm, you will create the 2 mm RBE. So this depends, right? If you don't know anything, just create the 2 mm by 2 mm by 2 mm or 3 mm by 3 mm, 3 mm, little bit something like this, but 200 micrometer, 100 micrometer like this, okay? But generally if you know by the SEM or by the something, by if you manufacture by yourself, you know this much approx 100 micrometer or the 2 mm or 1 mm is the repetition of the part, right? Did you get my point? So you know the fiber dimension, right? matrix dimension. So you know this repetition is continuous. So you can use this dimension. Accordingly, you can choose. Getting the point. Did I clarify?
Sir, let's say we are working on the 3D printing of composite materials. So what we are doing, we are laying up the plastic firstly, 4 layers, and then laying up the fibers.
Then you can choose the RBE, lamina RBE. Then you have a lamina RBE. That means when you create the RBE, you suppose create the 1 mm by 1 mm. This one, plastic. Top of that, what was there? Plastic one. Top of that?
Plastic, and then multiple layers of plastic, and then fiber, 1 or 2 layers, and then again plastic.
So then you can create accordingly the layer. Layered RBE you can create. So lamina RBE, that means that is a different way. Creation of lamina RBE. You can read in the Google.
But sir, we are not doing the lamina of the fiber, properties of the fiber lamina.
Okay, you have no laminas. Do you have not laminate?
No, we
Then?
are not having laminate. We are having filament.
Continuous filament.
Yeah,
Then you have two variation of a engineering constant through the thickness. You have to learn in the abacus. You have to give the subroutine. In this, when you put the fiber properties, this fiber only varies, right? Fiber only varies, no matrix. Matrix same, resin. So you have to vary the property from here to here. That subroutine is called the name of subroutine. If you search engineering constant variations according to a thickness, so you can vary the E plastic up to this thickness, E something like this thickness. So you can vary E from here to here according to your material. Getting the point? So this is your material properties of fiber you can give, matrix you can give. Do the same thing. You can do the mechanical properties, macro one and analysis, right? So the variation of the engineering constant through the thickness, which subroutine is work? I think if you search Google, it will give you the subroutine name. So you can vary the engineering constant according to thickness, right? That's the way to do that. I tell the name. I think VDE something your subroutine. I think this is locked. Can you open this? The name of subroutine is something UDL I think something like that. I will check this. See the name of the subroutine. Changing the thickness, changing the modulus, variation of thickness in abacus subroutine. The subroutine is name. Here is the subroutine name. Deload subroutine. Not deload. UEL. You can search here the subroutine name. Assigning thickness to cell faces. You are changing the modulus variation of thickness, right? Here you can get some solution, but it can be done. USD FLD. USD FLD. Okay, this one. You can go through this. USD FLD. Okay, that means USD according to field. So USD FLD is a subroutine you can work with. Okay, the name is USD FLD. Okay, so I think it's covered to you. Okay, you can vary this only. Suppose in his case he knows the fiber properties directly. One. For your case you need to change the properties by thickness. Okay, USD FLD you can use. Getting the point? At this very simple subroutine you can get the script of subroutine. Just change your properties only and put into the, and you know the subroutine installation. Install it and assign it and run it. I think it's finished now. Okay, thank you very much. Thank you. So have a nice learning.